Dr. Wada, please start.
Okay, thank you so much for the invitation. It's a great honor to present our result or our work. Today I'm going to talk about the Argon detector for dark matter searches and some additional in the future. Okay. Which way? Okay. So here's my outline. Just quickly introduce to dark matter, just in case someone doesn't know, or like a student or postdoc. And then go to a dark side program, and then discuss with our newest, but a little bit old, 2 years ago, the result on low mass WIMP search. And then discuss in the future the upgrade of the Dark 50 and then a future possible low mass WIMP search detector. And then move on to the little bit different topic, but similar. It's a low background. The experiment is a neutron-less double beta decay search using the Algo technology. And then just one slide for medical application. Okay. So here's let me introduce dark matter quickly, just because most of the people knows. So dark matter discovered by the Zuki, and he's looking at the Coma cluster, galaxy of a cluster of galaxies, and then discovered the speed of their movement is not expected. It's too fast. Just expecting from the visible matter. Okay. And then Vera Rubin confirmed it with more the statistics and looking at the stars in the galaxy. That's a discovery of dark matter. See? And then the other evidence is coming from everywhere. Right? For example, cosmic microwave background. And this is anisotropy in the cosmic microwave background. There's a ripple of the matters. And then this ripple, to explain this ripple, you need to have the dark matter. So dark matter provide this potential well for this early universe and acting, matter oscillating inside it. Without the dark matter, it's hard to explain this CMB spectra. Another strong evidence is coming from black cluster colliding. A long time ago, the two clusters collide each other. And if you look at this in X-ray, you see the hot gas, and then that's the displaced with the center of mass that can be the indicated by gravitational lensing. So this is so dark matter transparent to each other, but the gas is not. That's why the gas is left behind than the mass of center of mass of the clusters. Okay. So this also without the dark matter, it's really hard to explain. So the explanation such as the modified Newtonian dynamics is a hard time to explain this phenomenon. Okay, so currently the most of the energy in the universe is not what we are made of. Okay, only 5% of the matter or energy in the universe is our usual neutron, proton, and electrons. Okay. And 1/4 is dark matter. Okay. So the large scale of the galaxy, large scale structure of inside of the universe indicate that this dark matter exists. So we are almost sure there's a dark matter or some sort of matter. And so the question is, what is it? Okay. There's a so-called standard model, the spectrum of the particles, and which they can explain the all phenomenology in high energy physics nowadays. Okay. And then recently the Higgs boson joined this spectrum. But if you apply all the requirements for dark matter listed here, right hand side, you can exclude all the entire spectrum of standard model particles. Okay? So that means once we detect the dark matter, it's immediately imply the existing of new physics beyond the standard model. Here's the possible candidates, just the popular ones, I would say. There's some others, but I didn't list it. So first one is actually not the dark matter. I included it because it's still, I think that's possible. So this is modified Newtonian dynamics. It's explain small scale, like galaxy size. It's pretty well. I think they're more than, better than standard dark matter halo model. But as I said, this is a hard time to explain the large scale the structure of a universe. Okay. So if we can combine them together, maybe that's the best way to go. But so far, not so many promising the theory for that. Only I can say, what is it? Superfluid dark matter kind of thing could be possible. And then the second one is machos. It's just regular planets and just a heavy object. But based on astronomy, and it's almost entirely excluded. Okay. And within that, the black holes could be, but the usual black hole is already excluded. There's a non-observed one, but it's too small. We cannot explain all dark matter mass with these machos. Only primordial black hole can be taken as a dark matter. The neutrinos, stellar neutrino is possible, and still, totally fine. I think that still there's the strong experimental activity going on. Okay. And then same for axions. It's the total variable, and it's the good candidate for dark matter. And then today we're going to talk about WIMPs, weakly interacting massive particles. That's one of the most motivated candidate, and that's the one that we're gonna discuss today. Okay. And recently, I just want to mention. There's the axion study in liquid xenon detector, xenon 1 ton, and they see something interesting. But, if I have a time, I have some backup slide we can discuss. Okay, so let me give you an idea how difficult this dark matter search is. So local density of dark matter we know based on the movement of stars nearby within the Milky Way, within nearby our solar system, okay? Perpendicular to our rotational plane. Okay? And then, so based on that, the dark matter energy density is 0.3. It's recently more like a 0.4. But if you integrate over the entire volume of Earth, you get only 500 grams. Okay? So this is give you an idea how tiny this dark matter is. So this is the dark matter search is a rare event search, and we need to make a low background as much as possible. Okay, so we're gonna use look at the Argon detectors. But before going to the dark side program, let me introduce why we're gonna use we are using liquid noble liquid gas detectors. So because it's dense and easy to purify, this is compared to, for example, crystals. Crystals, there's many experiments with crystals, especially low mass, the range. But once you create the crystals, you cannot improve. For example, if you create the bad crystals, you need to live with it. But for example, the liquid the detectors, you can still purify. You can circulate through the gas system and then purify. Okay, so this is a really big advantage. Within the dark side, we did the ones for the beetle, but this is really advantage, I would say. And also we can talk about the upgrade. And because we can do this upgrade because of this advantage. And liquid noble gas is a high scintillation and ionization yield. This is really important for lower energy threshold, and then make scalability, good for scalability. And then transparent to own scintillation. This is again good for scalability. And those three is applicable for single phase, but for the TPC application, the high electron mobility and the low diffusion is important. And also we can get the ionization signal, okay, and the application in a gas phase. And additionally, this is the most important part is there's the discrimination. So we can discriminate the electron against the neutrons. So neutron recall is more like a WIMP, the recall, WIMP signal. So we can get rid of the electron background events with using this one. Okay. And then this is true for both xenon and argon. But the xenon side is denser and radio pure. Radio pure means that there is no internal background. There is some, but no beta backgrounds, especially. And it's a lower energy threshold because of the absence of radio isotope. And then that low energy threshold means high sensitivity at the low mass winds. Okay. On the other hand, look at the argon side, the big advantage is lower temperature. This is good for purification. Radon cannot escape from a radon trap because of this low temperature. The time scale order is different. And then there is a stronger electron recoil discrimination based on the pulse shape discrimination. I'm going to briefly discuss the pulse shape discrimination later. But the disadvantage is there is an interesting electron background from Argon 39. It's a beta decay isotope. So that's the completely background of electron recoil. So. And then we need a wavelength shifter to shift the scintillation wavelengths to detect with the usual the silicon PM and then the PMTs. Okay. So that's the used to be, and then it turns out using this ionization only study, we can take advantage of lower energy threshold, and that's end up in higher sensitivity at the low mass. That's what I'm going to talk about. Okay, so let me introduce the dark side program. Okay, so as I said, this is a WIMP search, direct WIMP search experiment. Okay. We cannot detect the axion or something like that. We can, but we have a less sensitivity than xenon. And we use a two-phase Argon time projection chamber, TPC, not a single phase like the deep 3600. And our design philosophy is using active suppression of a background. We aim to operate the experiment with a background-free condition. So that means if we see something in our region of interest, that means we discover some the WIMP. Okay. So that's the philosophy of this program. Okay. Yeah. So the bottom left is a DarkSide 10. It's a 10 kilogram the prototype. It's almost 10 years ago, I guess. And then DarkSide 50, the middle one, is a 50 kilogram detector. It's still running, but it's end most of the program. And currently we are building a DarkSide 20K. It's total more than 30 ton, the liquid argon, underground argon, and the fiducial was 20 ton. Okay. That's coming. We are working on it. But today I'm not talking about the DarkSide 20K. This is a high mass WIMP search. And okay, so this DarkSide is located underground laboratory in Gran-Sassо in Italy. It takes 2 hours from by car from Rome. Okay. And it's a city below this big mountain, Gran-Sasso, beautiful. Okay. Shielding the cosmic rays. And then we have for active suppression, we have a bunch of the outer detector, but the inside this small TPC is the active volume. Okay, to suppress all background, we need so much outer detectors, but in the end, this inner TPC is our target. Okay, so here's the one slide of how TPC works. Okay. Let me see. I don't have a mouse. Okay. So right-hand side, on top, there's a PMTs, 19 PMTs, and the bottom also 19 PMTs looking inside the TPC. And we have at the side a reflector, the white one, and then copper filled rings. It's a orange one, okay? And we apply the electric field. Okay? So if you can imagine the dark matter comes in and kick the argon, and the argon recalls, okay? And create a scintillation or excitation and ionization. Excitation, they excite and create this first light, it's called S1. And then leftover ionization, drift up, electron drift up. And then in a gas phase, it creates a second scintillation, it's called S2. Okay. And the time difference between S1 and S2 gives you the depths of the events. And then light distribution among the top PMT from S2 gives you a XY position. So with TPC, you can reconstruct the 3D image of your events. And so the left-hand side, there is a waveform. The first peak is S1, and the second one is S2. This is this is opposite usually, and this is the image of a charge cell. And top one is electron recall, like the left-hand side. You see the electron, the alloys, the green alloys. This electron kicks the other electrons and so on to create a shower. Right? And the electron recall has bigger S2 with compared to the same size S1 but of the nuclear recall. Okay, so that if you compare the ratio of S1 and S2, you can tell the electron recall from the nuclear recall. Okay. And then in the argon, liquid argon, we have another separation. It's called the pulse shape discrimination. That means just you are looking at the pulse shape, you can tell which one is which. Okay. So electron recall has the bigger tail, you can see it. And then nuclear recall has no tail. Okay, as you can see at the bottom. So this is a big advantage in liquid argon only. So this is the main purpose using liquid argon. Okay. So here's the high mass and the low mass WIMP. What I mean. Okay. So this y-axis is the cross section, the dark matter with nuclear cross section. Okay. And then that means the go bottom means that it's hard to discover, okay, hard to detect. The less cross section, hard to detect. And the x-axis is dark matter mass. We don't know dark matter mass because we only know is the energy density, as I said. Okay, so high mass side. Because this fix what we know is the energy density. The dark matter mass increase. That means number density goes down. Okay. Then the rate with the given cross section, it goes down. Okay. So pushing down this the high mass range, you need the scalability, okay? And large target mass. Okay, so this is why the most most of the planned experiment for this region is a liquid detector. We cannot get the same sensitivity with crystals. It's too big to make such a crystal. But the left-hand side is a different game. Okay? So this side is what the dominant is energy threshold. Dark matter is the light in this side, and because the energy density is fixed, means lots of dark matter. But the game is if this dark matter, you can detect this dark matter or not. Okay? So to push this one, this side, you need a better energy threshold. Okay? So that's a different game, the low mass and the high mass. And then we're going to talk about the low mass side. Okay, so taxa 50, usually we use S1 and S2. But to lower the energy threshold, we use only ionization. Okay. So if we use the S1, energy threshold, it's at 6 kb nuclear recall. But if we use only the S2, because of amplification, we can go down to 0.4 kb nuclear recall. Okay. And this is possible because we have a good amplification and low background PMTs and so on. And of course, we use underground argon. That's suppress argon 39. I don't go through the detail, but we see even only one electrons inside our. We don't use that range, but we have a confidence we see the single electrons. So so this is just that we make sure that we get the correct energy scale. So energy scale is important when you model backgrounds. For numerical is the background modeling, and for electronical is for background modeling, because most of the background is electronical. Okay, so we're gonna use this energy scale to from moving from a simulation to actual what we see in number of electrons space. Okay, so we have Argon 37 peaks. It's just a coincidence, but we didn't know that there's that, but we used it anyway. And for numerical energy scale, that's the important when you calculate how much events you expect from dark matter, okay, WIMP. So because the WIMP is numerical, and then given mass, and then the velocity distribution, you can, with this energy scale, you can make a prediction how much you should see. Okay. So that's numerical is pretty important. Unfortunately, in Argon, we don't have that much independent calibration. Okay, so the bottom the plot x-axis is a kind of energy. Okay, we use this reduced energy because we want to compare with the xenon, and x-axis y-axis is ionization yield. Okay, how much ion you electron you create with a given energy. And so this is the kind of weak point of this analysis. But we use americium barium neutron source and amc neutron source, and they fit the continuum. Okay, so this is not perfect, but I think this is what best we can do without this independent energy, monoenergetic calibration experiment. Okay. So this is what we need to improve in the future. And the background model is that we fit the higher energy range and then propagate down to the lower energy range, what we are interested in. Okay. And we see some excess, but we didn't know that well at the lowest energy bins, so that we didn't claim anything there. So based on this spectrum, is the bottom plot, the black histogram is what we see. Okay, and based on that, we put the limit. Okay, so this is the bigger plot is a kind of old plot of what we put in our publication, and the right-hand side small one is updated one, and 0.1 ton, it's a much bigger 1 ton scale detector. Did the lower backgrounds, but because of xenon has a heavier, and then this range is WIMP is kind of similar size of argon, and then much efficient to transfer the kinematic energy into argon than xenon. That's why we have a better sensitivity, lower threshold. So this is what we published already, and here we are thinking to upgrade the DarkSide 50. So DarkSide 50, there is a crypto 85. Crypto 85 is a beta decay isotope, then we didn't expect this one, and we expect that this is coming from some air leak in underground Argon facility. And if we knew it, we could remove it kind of easily with cryogenic distillation. But anyway, there is this krypton 85 and right now in dark side 50. And we can remove this one by a small coal chop. I calculated how much charcoal we need, and based on the literature, it seems like a 10 gram or that order should be enough if we can cool coal chop well enough. So there is this possibility. Still, we can improve our purity of our detector. That's a strong part of our the liquid-based the detector. Okay. And then based on this calculation, we can improve some the kind of close to the order magnitude of the sensitivity. This is only estimation, but everything goes well, this could be possible. Okay. And this is just showing how we estimate the krypton 85, just from spectral fit. Argon 39 and the krypton 85 has a kind of similar shape, but the end point is different. That's what we can set the limits. Also, krypton 85 has some small branching ratio of decaying 2 decays, by 2 decays. And we can tag this 2 decays, 2 consecutive decays, and we can estimate this. So this the estimation is kind of agree each other. That's why we have a confidence that we have a much more krypton 85 than Argon 39. So this is a possibility, okay? But let me go through the future low mass WIMP search. Okay, so this is the we're currently thinking. What's the criteria for future Argon TPC? Okay. And so first of all, we need a low activity of Argon 39. Okay, that's must. We have a plan. Okay, and also low impurity. So that's give us a good electron lifetime, and then low rate of single electron events. Single electron events is I didn't explain. This the left hand side and then the far left side of the spectrum, black histogram, there is a big peak, you know, order 3 order magnitude high compared to other part of the spectrum. It's the single electron or few electron events. This is due to some electron release from impurities within argon volume. Okay. So that's we know the studying the time correlation between big events with this single electrons. Okay. So idea is the impurity capture the electrons from the normal big events and release later, just 10 or 100 microseconds later. Okay, so that's create the independent, the low energy, low number of electron events. So the lower the impurity, I mean the improve the impurity. Okay, low impurity means okay. So this is typo. The high impurity means low rate of this single electron events. And also ultra pure photosensors to not create the gamma events, and then pure crystal. So the idea, the right hand side is a kind of sketch of this idea. So if we can submerge everything inside of a liquid argon, the atom, AAR is atmospheric argon. Then we can get rid of cryostat. It's a cryostat is kind of dirty. So if we can put this cryostat far away from the sensitive volume, then we can reduce the background. Also, same idea for the silicon PM arrays. We can put aside, and then the number also make it smaller using a light guide. And yeah, so this kind of the detector might be ideal for this low mass study. Okay, so the key development is ongoing. This is partially mostly for dark side 20K. It's the high mass search, but the same technology with a small modification, we can adapt this technology to our low mass detector too. Okay? So silicon PM based the photosensors, and we can. The PMT is the kind of dirty things, and with the silicon, ideally, technically, we can clean it up, except the electronic part. So electronic part is currently limiting part, but if we use integrated electronics, and then we can reduce. And also with the light guide, maybe we can reduce the number of size of silicon PM with keeping the same coverage. And the second one is Urania. This is the underground argon extraction facility in the Colorado Cortez, Colorado in the US. And then this is already funded, and contraction is about to start. And the earlier is the cryogenic distillation column. Its idea is separate argon 39, argon 40 from argon 39. Okay, so this is a kind of sounds crazy, isotope separation. But with 350 meter column, big column within underground mine in Sardinia, Italy, this is possible. Okay, we are testing, and with the top and the bottom column, and the one middle the prototype. And then the results with nitrogen is pretty good. So we'll see how much we get, but this is currently ongoing. Okay, so with this idea of ideal setup with 1 ton year exposure, we can touch neutrino flux, neutrino floor, so-called. This is coming from coherent scattering of a neutrino from solar neutrino. Okay. And so I listed what we made assumption. I don't go into detail, but this is the possibility. Okay, so this is another assumptions, lots of assumptions. But to do that, another things we need to do to going forward is this ionization calibration in a lower energy. This is difficult, but that's what we need to do. Nobody knows what happened at lower energy. We assume a flat, similar to assuming a similar behavior with xenon. There's no reason that we are different from xenon, but might be something. But so definitely we need to have a calibration point. And for that, we have some experiment within the collaboration. This is the small TPC detector on beam, lithium beam, and creating the colliding with the target, and then make a new monoenergetic neutron beam. Okay. So with knowing the incoming energy and then the recoil angle, you can calculate the recoil energy. So this primary goal of this experiment is not the calibration. This is the directionality of the nuclear recoil. So this is the low energy the nuclear calibration is not yet done, but to me this low energy nuclear recoil measurement is more interesting. So, but it's coming. Okay, so this is ongoing measurement. Okay, so this is an overview of the facility, and the left hand side is a small TPC with a silicon PM readout. Okay, so let me go to the more wide step. This is we are start thinking, you know, what else we can do with liquid argon technology. Okay, so one thing is maybe we can do neutronous double beta decay. Okay. So right hand side there is the Majorana mass versus minimum the neutrino mass. Okay, lowest one, and there's the possibility inverted hierarchy and then the normal hierarchy. Okay, and right now this I took from EXO paper collaboration. So the top blue and the green one band is already measured their result, and the pink one is next generation NEXO. Okay. And then our question is, what kind of detector, or can we do the double beta decay completely exclude this both normal hierarchy and inverted hierarchy? What we need, okay, that's what we want to answer. Okay. So to reach this the Majorana mass of 1 milli electron volt, we need to set the limits in half-life to 0.4 to 2.8 times 10 to the 30 years. Okay, to get this limit, we need 670 to 4,800 ton year of background-free exposure. If there is a background, you need a more exposure. Okay, so just background-free means that at the maximum, I mean at the minimum, we need this much exposure. Okay. And we did some study. Is it possible, and what we need? Okay. So first of all, liquid argon doesn't have a double beta decay isotope. If you to do that neutronless double beta, you need a double beta isotope. You know, isotope which do double beta decay. Okay. So we need to dope xenon 136. Okay. And this idea is doping this isotope inside of liquid argon. This is kind of, if you think about it, it's a similar idea, like the other Gelda experiment. The Gelda experiment, they submerge their crystal into liquid argon. Okay. In our case, the target is xenon 136, and submerged into the argon. Okay. But it's kind of mixed already. And our energy resolution is slightly better than EXO 200. And without the deep tuning, we do some calibration, but not the deep tuning like EXO 200. So we get the good energy resolution already, but not good enough. But we need the better tuning. Right now, for this study, we assume a good energy resolution without any the supporting evidence. Okay. And a big advantage is coming from colder temperature with the liquid argon. With the colder temperature, the argon trap is much efficient. And not argon temperature, radon trap is much efficient. And there's the dangerous daughter, bismuth 214. It's the similar to our region of interest. Okay. So getting this radon is pretty important. Okay. And then the other advantage using a liquid argon, lower temperature, is a SIPM operation is much easier, less noisy. And then it's half advantage is we have a liquid argon, so the lighter target means gamma can travel farther. Then that means gamma background can scatter twice, and we can resolve it. In the xenon, it's dense, and mostly the gamma background deposit energy in the same site. Okay. But on the other hand, that means the xenon, pure xenon detector has a much more stronger self-sealing. So this is the kind of balance you should consider. Okay, so here's the background that we need to consider. Neutrino. Okay, the inverse beta scattering happen. Okay, so neutrino, we cannot seal it, so we need to somehow reduce it. If this rate is too high, this is disadvantage for us, because argon can also create this scattering. Inside argon, we can use it. And then, of course, double beta decay tail. To exclude this, we need a good resolution. And cosmogenic activation of argon and xenon. They usually create the beta background, and then that's limit our sensitivity. So we did this, each one of them estimate. Okay, and the setup is like this. So I don't have a time, so I don't go through detail. Okay, just flashing the result. And this is what we get so far. So what this is a 30 centimeter cut, a fiducial cut each side, and the still 50 ton xenon 136 fiducial. The most dominant is inverse beta scattering backgrounds. Okay. It's much more than the other contribution. Okay, so based on that, we can get this possible sensitivity. Okay, but this gray band shows you what we need to reach to eliminate exclude all down to the 1 MeV. Okay. So it's a little bit less still. Okay. Okay, so that's a neutronous double beta decay. Just started the idea and the sensitivity study. And this one is the medical application. This is liquid argon. This project is still, it's already started in Princeton. And I got the funding in Italy with the 300K to make this prototype of this. And the same idea, silicon PM, liquid argon, the cryogenic the technology, and we can contribute to society also. Okay, this is it. Okay. Summary, I hopefully the convince you or the give you an idea the liquid argon might be a possible target for low mass wind range. And the technology is there, or we are developing it. Okay. And the low energy nuclear recall calibration measurement is necessary, but it's planned. And the other the physics, maybe we can contribute. Okay. Also the medical application. Okay, that's all. Thank you.
Okay, thank you very much. This was very informative and interesting.
Sorry that it takes too long.
No, you're just in time. So just even less than 1 hour. So I apologize for this disturbing event we had. It turned out that a name which was used to bomb you was a name of our colleague who actually was hacked. So his account was hacked, so we realized that, and so he also apologized for this event. Okay, so this was the first time actually in the series of our seminars.
Me too.
Yeah. Okay. Nevertheless, I think we quickly removed this guy. All right. So yeah, please questions, Evgeny, please.
Oh, sorry, my mic was off. Sorry. So my question is: it seems that you have much more events in low energy region in compared to xenon experiment. Just
yes. So yeah.
Do you have any explanation?
So
your effect is not 3.5 sigma, but like maybe 20 sigmas.
So do you see my screen? Okay.
Yes.
So this is the comparison I have long time ago. I mean, this slide is kind of old one. The comparing the Xenon 100. This is the one generation older detector they have right now. Right now is a Xenon 1 ton. Okay.
Right.
So you can see this is the top left, and red is a dark side 50 hour spectrum, and then the black one is a Xenon 100. Okay. So most of the space, I mean spectrum, energy range, they have a lower background. Okay. But in the lowest one, we have a lower. And plus this, the right, the bottom one is the WIMP spectrum with the same mass, same WIMP mass, and the same cross section. Okay, even the same mass WIMP, they create a more high energetic recall inside of Argon, because Argon is a similar mass of them. The Xenon is too heavy. Okay, this two combination creates our sensitivity. Our sensitivity is better than the Xenon. Okay, and then if you remember the 1500 events per keV EE per ton per day. Okay, so I just compare the bottom of our spectra to the next slide. Okay, somehow I cannot go back. I cannot go back. Let me see. Yep. Okay. So this is I did for myself, so please look at the right hand side. So this is Zenon's S2 only ionization only study. Okay, and it's a bit hard to see, but on top of the top the plot, and the y-axis is the ton events per ton day kb. That's we have the 1500 events. Okay, so here they have only one event, less than one. Okay, most of the space. Okay, it's a little bit high energy, but in high energy there's a lot less. Yeah, because they cut the kind of the severely, but still the 3 order magnitude or less.
Sorry to interrupt you, but so you want to say that effect is real? So what Xenon sees is really axions?
No. This one is sorry. The mix. I thought that someone might ask what I think this axion excess. But so
no, because you also have excess. So maybe can you say that yes? Can you sort of confirm that Xenon data is?
So the first of all,
what is your opinion? Is it background? Is it really axions?
To me, I thought they say there is a possibility, still possibility of the tritium. Okay, so because there is no way they can constrain the tritium contents. I think it's a little bit hard to say. It's a little bit weird. They said they see excess because for back you cannot constrain the background because of a tritium. So to me, a little bit the weird. But based on their study, the first of all, our axis and then their axis is a different place. So I don't think there's the same thing. Okay, and our axis is kind of really lowest energy, and then I don't think that we want to claim anything. Okay, and to me the excess is could be axiom, but the most likely background, just the background, or more like they use this energy variable that you combine S1 and S2. That creates some bias, and they don't have the calibration point on this lowest energy. So that's the most possible explanation. And yeah.
Okay,
so, but yeah, I would say.
I have another question. Can I ask? So another question is, so everyone, when we speak about background, people mention lead-210 and other components, but no one mentioned carbon-14 from organic. Do you expect any organic in noble liquids?
I don't think so. I don't. Yeah, I don't think so, but I don't know why I don't think so. That's a good question. But carbon-40 is, I don't remember the endpoint of
is relatively low endpoint, so it can produce some excess in low energy region.
Yeah, but for the xenon, at least they did really good distillation and purification. So I don't think but I don't know, the trace level maybe. I have no idea.
But we now speak about this 90 events per ton year, so it's really small. So
yeah.
I think even trace presence of organic can produce some excess.
Yeah. I think the more expert someone can. I can bet they think about it, but I don't personally don't know.
And so maybe final question, if I can. Dmitry, can I ask more questions?
Yes, please go ahead. No problem.
So the final question is that now all experiments, when they consider this low energy parts, they have to take into account this Migdal effect that can produce additional energy.
Mm-hmm.
So do you take into account this consideration? What your expectation in your case for argon? Will be it significant, not significant?
Yeah, so that's there's some group that within the collaboration, they are looking at this Migdal effect.
Mm-hmm.
And then if they're more like if we include the Migdal effect, how much we can tighten the constraint. So if there's a Migdal effect, that's always plus, more ionization. Okay, so more sensitive to our the WIMP, the signal. Okay.
Yeah, do you think that what xenon C, maybe this is a result of this Migdal effect?
No, this is too high. Migdal effect is much lower.
Okay.
Yeah. And yeah,
So
I think that's we can say. Yeah. One thing they didn't. I think in a presentation they didn't emphasize, but this is what they have for their ionization yield study. So this right hand side, but the same data for the excess. If there's excess, you see this this component. It's so this is what they see. So it's consistent with S2 only, but it's hard to conclude this one.
okay.
Most likely, my honest opinion is a background, but yeah, we'll see.
Okay, thank you a lot for your explanation.
Thank you.
All right, thank you. Any other question, comments, please? Yes, Konstantin.
Okay, can you hear me?
Yes, we can.
Yeah, sorry, maybe I missed something, but when you are speaking about double beta decay,
Yeah.
you are speaking about enriched xenon, which you want to add. So xenon 136.
So we.
Yeah, but yeah, sorry, just a question. I don't know. Maybe please do not understand me wrong. I want to be as correct as possible. But do you think it's very interesting and very useful, this estimation? But let's say, how serious is it? Because the enriched isotopes. To be more clear, I am from Gerd and Legend experiment.
Mm-hmm.
So. Yeah, I just want to understand there are quite some proposals which are going to work with enriched xenon, and I'm afraid that it's really just not possible due to the lack of enriched xenon for all of these proposals.
Yeah. So first of all, if all proposed experiments happen, we don't have that much xenon.
Yeah. That's what I mean. So, what do you think about this simple?
So that's the kind of a little bit the political the question, and I think that in the end, I think the most possible experiments should happen, and I think we everything cannot happen. So, and then for enrichment, how are we gonna enrich this big amount of xenon? That's a question. Okay. So what we're thinking is same technology is this ALIA, the cryogenic the separation.
Mm-hmm.
But we need even longer column for this separation. That's for sure. But that's the idea. You know, the same the isotope enrichment technology we might use here too. Okay.
Okay, very interesting.
Yeah. So this is a kind of, you know, first of all, first step is the liquid argon enrichment, the elimination of argon 39. You know? Then if that's the successful, we can upgrade the column for this. Okay. So this is kind of step, and that's the in our mind. And where we can get the xenon, that's I think we need to ask someone else.
Yeah. I see. So, no, I just want to say that it's so pity for us, because first time I hear about such a program, because I thought after you produce enriched argon, depleted, let's say, argon, out of argon 39, you will give us this column to legend experiment. We also need it. But now I see we start to be somehow. Yeah,
but I think no. I think that we need to make a new one. Actually, the same technology, but the new one for xenon enrichment. I think, but I don't know. I don't know. Sorry. Yeah.
Okay. Thank you very much. Very interesting. Yeah. Thanks a lot.
Yeah. Thank you. Another question? Comments? Yeah, I have one. Maybe can you show again us the comparison of liquid argon technology with other technologies?
This one? Or?
No, in terms of dark matter sensitivity.
Like this one? This one? Or?
I think it's
sensitivity. Okay,
sensitivity
to
cross
this one?
Yeah, something like that. Yeah. So here you put not, I think, not every experiment. I'm just wondering where in this graph, say, Edelweiss is placed.
Edelweiss is the kind of left, the top one. The Edelweiss is low mass experiment. They have a much the lower sensitivity. So
Dmitry, can I answer?
Left.
Yeah.
So,
I'm just curious how they compare.
We just published this at the region of 1 MeV mass.
Yes, and so what is your sensitivity?
This is how to, it started from 0, like from 10 MeV.
Yeah.
And we published from below 1 MeV.
It can go much lower.
Really low mass. And
so
recently, of course, our sensitivity was not so huge because mass is small. So, in region, let's say, in 1 MeV, depending on what kind of light-heavy mediator we consider, then sensitivity is like on the region 10⁻32 centimeter square. So it's much higher and much on the left.
32.
Yes.
3,
yes,
2.
Of course, mass is small. Yes, of course, if we go to higher mass, like 10 MeV, our sensitivity start to improve, like to 10⁻34, 10⁻35. But of course, we cannot compete with this huge experiment, 1-ton experiments. Our mass is mass of bolometer is like 1 kilogram.
I see.
So we competitive in the region on the left, but of course, in terms of sensitivity, we cannot do like 10⁻50. No way.
No way. Okay.
So to be fair, this threshold right now is two number of electrons. 2 electrons is a kind of extent. So this is what we hope we can get. So the left bound is kind of what we hope to get, to be fair. So that side, we don't have a competition.
Mm-hmm. So dark side cannot go to as low masses as Edelweiss is doing. Is this correct? Can you hear me?
All this is very interesting for us. So thank you very much.
Thank you. Thank you, Oleg, also. They invite me here.
Yeah.
Okay, sorry, I had an internet issue, so very lucky that it is still ongoing. So any other questions, please? Comments? No? All right, so then probably we have to conclude and finish the seminar. So thank you very much. This is very interesting seminar and very interesting and important work.
Thanks so much.
Yeah, thank you very much.
Thank you.
Yes, bye-bye.
Bye.
Bye-bye.
Bye-bye.